Good afternoon, everyone. I am Yang Li from Tsinghua University. Today I am giving a talk about a paper titled Dissecting and Streamlining the Interactive Loop of Mobile Cloud Gaming. Recent years have witnessed the emergence and prosperity of cloud gaming, which enables high-quality gaming experiences on mid to low-end devices. To achieve smooth gaming experiences, CG platforms are expected to provide users with a high media streaming bandwidth and a low interactive latency, within about 100 milliseconds. Here, interactive latency is the delay between a user input action and when the game's response to that action manifests at the client. Obviously, it is the key metric of cloud gaming apps' quality of experience. Actually, cloud gaming apps can be divided into two categories. One is cloud gaming for mobile games, like COD Mobile. We call it mobile cloud gaming, or MCG for short. The other one is cloud gaming for console games like GTA 5. We name it console cloud gaming, or CCG for short. Currently, CG's interactive latency has not been well understood by both the community and the industry. It is more than network latency due to the complexity of cloud-side processing. To understand the status quo of CG's QoE, it is necessary to accurately measure the interactive latencies of commercial CG platforms. However, it is quite challenging, given that CG involves complex interactions among multiple agents, including user equipments, network, and cloud servers. Besides, almost all commercial platforms are closed source, and open source solutions for cloud gaming often lack representativeness. Given the above concerns, we measure the interactive latency of a platform from the outside in a record and recognize approach. As listed, we study 8 representative cloud gaming platforms that are popular in either the USA or China, using 100 mobile devices geo-distributed in both countries. Among them, 3 are CCG platforms, 3 are MCG platforms, and 2 support both. To conduct measurement, we first use high-speed cameras to record videos of user interactions with games with an ultra-high frame rate of 2000 FPS and full HD resolution. We position 2 cameras in front of and at the side of the device screen, respectively, so that both user actions and visual game contents can be clearly observed. We select specific interaction patterns for each game, for example, invoking game menus, changing views, or touching in-game buttons. They are performed with styluses instead of fingers to ease detection. After recording, we examine each frame with the segmentation anything model to detect and track objects in the frames. In this way, we can recognize the starting and ending timestamps of a user interaction. Then the measured interactive latency is calculated as the difference between the 2 timestamps. Further, we are curious about the network impact on the interactive latency, since this is what common users are the most concerned with. To address the concern, almost all the commercial cloud gaming platforms have on-screen widgets presenting the real-time network latency via their client apps, which greatly facilitate our recording the network latency. Since a low network bandwidth can also lead to high interactive latency, we periodically record the downlink bandwidth with a lightweight Android API in the meantime. Finally, we obtain over 20,000 valid records, which reveal quite a few surprising results. First, we find that the interactive latency of today's MCG cannot meet user requirements. All these studied MCG platforms suffer from undesirable interactive latencies, while the performance of CCG platforms is much better. We attribute the above to the more complex processing logic of MCG compared with CCG. That is, the mobile OS virtualization especially required by MCG. Given the poor driver support of desktop GPUs in mobile operating systems, there actually exists a gap in rendering performance between CCG and MCG backends. Second, contrary to most users' common beliefs, most of the excessive MCG latency is not attributed to the network, as shown in the figures. More in detail, no matter which RAD is used, the network latency only takes up a small portion of the interactive latency. The network latency is pretty low in most cases because all our studied platforms have deployed geo-distributed cloud servers across either the USA or China. Besides, we observe that a lower network delay does not necessarily translate to a better interactive latency. And regarding user request workload, we find that there is no significant difference between the interactive latencies during peak hours and non-peak hours, revealing that today's MCG platforms possess sufficient scalability to serve a fluctuating user request workload. As for the game workload, we know that on all MCG platforms, simple 2D games with light rendering workloads suffer from higher interactive latencies compared with graphics-intensive 3D games. According to existing documents of some MCG platforms, we suspect that this might be owing to unbalanced resource allocation strategies. To discover the root causes behind the above observations, we first explore the mobile graphics pipeline. The graphics pipelines of mobile operating systems consist of multiple stages due to the user's diverse needs for graphics. Each stage performs its unique functionality. When a game is played on an Android device, for instance, the game is typically the beginning of a graphics pipeline. The game performs graphics rendering by writing its contents into a frame from a buffer queue termed surface. At the same time, other system apps, like the system UI, may render contents into their own surfaces. Various surfaces are connected to a compositor called surface flinger, whose job is to merge the contents of individual surface layers into one or more graphics frames for display. The composited result is then sent to the hardware composer module, which submits the contents to the actual display hardware. It is worth noting that the stages usually work in their own paces, which can cause frame access issues. For example, while Surface Flinger regularly conducts layer composition at the refresh rate of the display, the pace of game rendering can be rather uncertain. When the game delivers a new frame to Surface Flinger while it is compositing, the composited result may contain portions of multiple game frames, leading to the screen tearing problem. To address screen tearing, modern mobile operating systems typically adopt the vsync mechanism. This figure presents an example of the pipeline from stage C to D before Android 4.1, where frames are displayed with vsyncs, but drawing is processed without vsync. In the first iteration, the screen displays frame 0, at which time the GPU and CPU render frame 1 and finish before the screen displays the next frame. Because of the timely rendering, the buffer is swapped before frame 0 is displayed, which is after the first vsync. And then frame 1 is displayed normally in the second iteration. Then frame 2 starts processing, which is not until just before the upcoming second vsync. When the second vsync comes, the buffer is not swapped because frame 2 is not ready, so frame 1 is still displayed. This situation is named junk by Android developers, which means a frame drop occurs. We can see that when frame 2 is ready, it is not displayed immediately, but waits for the next vsync to perform a buffer swap before displaying it. In this way, screen tearing can be avoided, but the uncertain drawing paces cause frequent frame drops. To improve the display performance, Google has reconstructed the Android graphics system since Android 4.1. As soon as the system receives the vsync event, the CPU and GPU will start rendering the next frame immediately. As a result, frame drops can be significantly reduced. Overall, vsync works in an event-driven manner. Frame consumption is triggered periodically by vsync events at a pace specified by the consumer. In each period, when the producer finishes frame production, it waits for the vertical blanking interval, which is the time interval between the end of a production and the next vsync event of the consumer. As shown, vertical blanking intervals create uncertain latencies, and the latencies can accumulate in a lengthy graphics pipeline, leading to unsatisfactory user experience. To further diagnose MCG's undesirable interactive latency, we contacted the developers of the measured commercial MCG platforms. Eventually, the developers of XMCG agreed to share their design and collaborate with us to diagnose the undesirable interactive latency atop their platform. The high-level interactive loop of XMCG is shown in this figure. As shown, a total of 5 vsync events exist to synchronize the paces of different stages in the graphics pipeline. The interactive loop of XMCG comprises as many as 16 stages, including 5 vsync events. It involves complex interactions among multiple agents, as shown in this figure. Among the 16 stages, we want to uncover which ones contribute the most to the interactive latency. To this end, we conduct an in-depth measurement study on the end-to-end loop of XMCG using 10 mobile devices, whose operating systems are tailored for detailed latency recording. To precisely trace the data flow of a specific game frame in a lightweight manner, we measure passively by instrumenting relevant system modules and recording the timestamps of relevant network packets. We classify the delays of the measurable stages in the loop into 6 categories, including network, vsync, game rendering, layer composition, video processing, and others. Results in this table show that in terms of mean latency, the vsync mechanism contributes the most to the non-network latency. Here, non-network latency equals to the interactive latency minus network latency, even more than game rendering and video processing. So how can we minimize the vsync-induced delay? Are these vsync events all necessary? Is it possible to disable vsync? To answer these questions, we delve deep into the loop and discover that 5 vsync events are tightly coupled with other stages. Vsync 1 has been built into modern game engines like Unity and Unreal. Vsync 2, 3, and 5 are required by core graphics modules of both cloud-side and client-side Android systems. Vsync 4 is necessitated by the video encoder to encode videos at user-defined frame rates. Fortunately, while all the vsync events are structurally required and are hard to disable from the perspective of an MCG platform, not every vsync event is functionally useful. In the context of MCG, games are usually the only foreground apps besides system UIs, so layer composition and virtual display in the guest Android system only append game-irrelevant system UIs to a frame in almost all cases. Thus, these stages, along with their vsync events, are functionally unnecessary for MCG, as the game frames are ready to be displayed on the client after game rendering. This motivates our attempt to bypass some vsync events and decouple game rendering from the latency graphics pipeline, hoping to avoid or reduce the impact on the interactive latency. Guided by the above insights, we designed LoopTailor, an adaptive vsync regulator. This figure shows the architectural overview of LoopTailor, which streamlines the interactive loop of XMCG by cropping the cloud-side graphics pipeline and staging it to the client-side pipeline in a fine-grained manner. LoopTailor has 2 components, game frame interceptor and remote vsync coordinator. To realize low overhead frame interception, game frame interceptor breaks the virtualization boundary and captures game frames in place. This figure shows the workflow of GFI. The core idea is to leverage cross-layer information from both the guest system and the host virtual GPU to intercept and forward handles, so as to minimize data copies. Due to time limit, please refer to the paper for implementation details. With the game frames intercepted, stages 6 to 9 in the original graphics pipeline can be bypassed. RVC aims to align the remaining 3 vsync events. As vsync 5 is controlled by the client OS and cannot be changed by a user app, RVC proactively synchronizes the timing of the cloud-side vsync 1 and vsync 4 with the client-side vsync 5. To this end, RVC first obtains the timing information of vsync 5 from the Android frame pacing library in the client, and then predicts the delay of each intervening stage between vsync 1 and vsync 5. There are 4 stages happening between vsync 1 and 5: game rendering, frame encoding, network transmission, and frame decoding. Although the latency of each stage can be independently forecast as a time series and summed directly to get the overall latency, the prediction result is oftentimes highly biased due to error propagation. So to minimize the prediction error, our key insight is that the stages have latent correlations within the end-to-end graphics pipeline. Therefore, we adopt hierarchical time series forecasting based on the Minty approach, given that the involved latencies can be hierarchically organized as shown in this figure. Details about the forecasting, please refer to the paper. With the predicted latencies in hand, the paces of vsync events can be adjusted in a synergetic fashion. As for vsync 4, the core idea is to decouple frame encoding from vsync 4 events to reactively encode ready-to-consume frames in time. When the cloud-side game frame rate is lower than or equal to the client-side video frame rate, all produced game frames need to be encoded for streaming to satisfy the client-side requirement as much as possible. Otherwise, the forecasts are used to determine whether the encoder should encode or drop a game frame. Collaborating with XMCG, we deployed looptailor on their cloud infrastructure. We also compare looptailor with other representative MCG platforms, including Tencent Pioneer, NetEase Cloud Gaming, JoyArc, and CloudMoon. And the measurement settings and the evaluation settings is the same with the measurement settings. As shown, looptailor yields the lowest average interactive latency as well as the non-network latency among all platforms. We also evaluate the performance gain brought by each module of looptailor by enabling them incrementally. Results demonstrate both GFI and RVC are essential for looptailor. And that's the end of my talk. Thank you for listening.